Welcome to this tutorial about vector math. So in this tutorial we will be going through a little bit about how you calculate and determine vectors and just general math when it comes to 3D space in a game engine, which is very useful and often comes up. So my hope is that this video will cover most, if not all, of your needs when it comes to understanding why you do certain operations and how you do your calculations to get the desired result that you're after. So let's jump into it. So here we are inside of Unreal Engine 5. Now this of course will work just as well in Unreal Engine 4 because vector math is the same everywhere. And what we have open here is Unreal Engine 5 Early Access, and the interface might look a little bit different if you're using Unreal Engine 4, but I think you should follow along because most of the stuff that we will be doing will be in blueprints. Anyway, so I have a third-person character template open here, and we're just going to be removing some of the scenery here so we have some more space. And what we have here is a character which we're going to be placing at position x0 and y0. So he's in the center of the map now. Now we're gonna be creating a class to help us along with this. So we're gonna be creating a subclass here called a child class from our third-person character, and we're gonna call this the child character. And this is because this character we're going to be using as our reference for our calculations to make sure that we understand what is going on. So to begin with, we're going to place this character at position 400 when it comes to x and position 800 when it comes to y. Now, a common thing that appears is you want to find out how far away is something from something else. Now, most of the time when we're doing our calculations, we're going to be knowing a few things. We're going to be knowing something like the character that we are and its location. So we have its X, Y, and Z. And we're gonna know our target's location. So it's X, Y, and Z. And using these numbers, we're going to figure out things like distance and such. So if we start with distance, and hopefully you remember this from trigonometry, or if you are not that remembrant about it, or that you can't recollect it that well. The distance when it comes to, okay, my mouse cursor here isn't super visible. That might be a problem. Let's change the material over here to something that's maybe a little bit more helpful for us. Is this gonna be good? It's not great, but at least it's something that doesn't let the mouse cursor blend in too much. Anyway, so we have this character over here which is standing on x0 and y0, and we have this character over here which is standing on x400 and y800. So to be able to calculate the distance here, we are using Pythagoras' equation or theorem. I'm not sure what it's called in English, but anyway, it is the ability to calculate the hypotenuse. Anyway, we are able to figure out our x-axis here in distance by using our x value here and this x value here. So since this one is in position 400 and we're at 0, that means that if we take 400 minus 0, we get a distance of 400 in between us in x. Now when it comes to y here, we can do the same thing. We're at 0 over here and this one is at 800. Actually, this is I'm lying to you, because as you see down here by the gizmo, the y direction is actually the one that's 800. It's the one that goes in this direction, and the x direction is the one that goes upwards here, and that one is the one that's 400. So we know that the distance here is 800, the distance here is 400, and using that we can use the mathematical equation of taking the y direction here, or the y length, and having it with the power of 2, and also using the x direction with a power of 2, and then having the results square rooted out to find out what the hypotenuse, what the length is, the distance. Now, that's just the basic math behind it. We don't really need to know this because we have some tools available to us. So if we start off with our third-person character here, let's do some simple stuff here. I went into the child character. I want to be in the third-person character because that's going to be our reference as our who we are. I'm just going to make sure that this one is being possessed by player 0 also, so that when we're starting to play and testing out our values, we will be using that character. So that's why I chose to possess this character over there. So we go back to our third-person character. Now, let's make a begin play. The reason we do this is because we want to have a reference to our child character, because we're going to be doing a few calculations with it. So we're going to do that actor by class. There's only one, so we can take this one, and we're going to choose a class here of child character. So this is our character. Actually, yeah, it'll be fine. So this way we get our character that we're interested in promoted to a variable. That's not the one I expected. That's a little bit different. Not sure why it's doing that, so let's just do this. Let's call this child reference. We'll do set like this because this is more what I'm used to seeing. Anyway, so at the begin play we're gonna find our actor to our child character and we're gonna get this reference, so we have it for later. And then we're gonna make a custom event for a key. Actually, we're gonna make keyboard E. Let's see if we can find the E key here. Like so, and this is gonna be our execution event for triggering different things like checking up if the math is working as we're expecting it to and such. So we have our own reference. So get actor location. This is the location of our character, so the third person character, the one that's 0, 0. And we can use this distance or this position and just type in distance, and it will say put in 2 vectors and you'll get a distance. Now let's go back a little bit here. This position over here is a vector because it consists of an x, y, and z. But a vector can be both a location and a direction length in 3D space. We will be touching upon this many times during this tutorial, of course. So if you don't get it at once, it's fine. You will hopefully get it by the end or during the course of things. But so if we take this character over here, he has a vector that shows off his position is 400 and 800, but it could equally mean that these values represent a length direction from the center up to this point as well. They are interchangeable in that way, and we're gonna make use of that with our calculations later on as well. But just like something to plant a seed in your head right now that they're both things, in case you were not aware. Going back to our character now, we can see that, okay, we have a distance node available to us here, which can take 2 inputs, and then it returns a value here. So we get our child reference, and we get its actor location as well, like so. And then we decide to actually make a print, and we print out our value over here. So if we start to play now, we know that that character over there is 400 away in X, it's 800 away in Y, and if we press E now, you can see that it's calculating that to almost 900. To make this very simple, we can just take this character and reset its Y value, so it's just 400 away from us now. We start playing again, we press E, you can see it says 400, because now it doesn't have to take into consideration X or Y and Z, it only has the X value. And the Pythagoras theorem equation allows or ends up being just the same as the distance here, because we're not actually like making a triangle anymore, or a triangle with one side that's very, very thin. Anyway, so that node is what we're going to be using when we want to find the distance to something. And this value that we get here is a float value, and the float value is the value in Unreal units. And Unreal makes use of the metric system, which means that in this case 400, if we go back and look into the map here, this is actually 4 meters or 400 centimeters. So that's what you will be getting when you're working with floats when it comes to the X, Y, and Z grid. So this is distance. Let's make a comment. This is how you calculate distance. You take 2 different locations, you run it into the distance node, and then you get a distance in Unreal units, which is centimeters as a result. Okay. Let's move on to the next part. The next thing that is very useful to know is how to calculate a direction. A direction is a relationship between 2 different points. For example, if we go in here and we know our character over here is at 0 and this character is at 400 when it comes to X. We don't have to take into consideration right now the Y and the Z for this simple example, because they are the same. So the direction for this character to this character is this character's location minus this character's location. So let's test that out and see what I mean. So if we take, like before, these things, we take our target, the one we're trying to find the direction to, and then we subtract it with the source, which is where we are, and then we print out that value. What we're going to be getting is this. You see 400, 0, and almost 0 in Z. So this is what's called our direction. Now you can see that it has a length in the type of X is 400, which means that our direction vector has 400 in length when it comes to that specific axis. Generally, when you're working with directions, you don't want to have a length. You want to have what's called a normalized vector. And if we were to take this value and type norm, we get normalize. Then you get the tolerance value, which is basically saying how precise it should be. And if we decide to print out this value instead, you see that we get this result. You see it has a value of 1, 0, and 0. Now, if I were to change this character's position over here, so it was to be 400 in the Y axis as well, and we play, you can see that we get a value that says 0.7, 0.7. The reason for this is a normalized vector is a vector that has all its axes in a range between 0 and 1. So 1 is the highest value it can have and 0 is the lowest value it can have. It can theoretically be -1 actually also, but 0 to 1 is the scale that it generally goes to. For our simple example, it will be that. Minus just means in the opposite direction. Anyway, so what's happening here is we're again having the direction the directionality here calculated as the value in x becomes 0.7 and the y, actually this is the y, is 0.7 and the x is 0.7. You might be thinking, why is that? Why isn't one of them 1? Well, that's because the direction between this person, this character, and this character, that's the distance that is 1. So this is Pythagoras' theorem in reverse then. It's calculating if the hypotenuse was 1, what are the lengths of the sides gonna be? And the lengths of the sides are gonna be, in that case, 0.7, as you see there. Now you might be wondering, what is the point of having a normalized vector? What is the gain of doing that? Well, for one thing, when you're working with something like this, when you have inputs, the movement input over here that's taken from that's handled by the character movement and the pawns, these are vectors that are normalized. They are between 1 and 0, or 0 and -1, depending on which direction you want to go. And they don't have a length. So for these cases you want to have a normalized vector. Also, another reason why you would like to have a normalized vector is because you want to do some calculations for this. For example, if I was this character and I wanted to do a charge attack against this character, but I wanted to not only charge into him, I wanted to charge into him and past him. So like, let's say 1 meter past him. So then I would want to calculate, okay, which is the direction that I should be going to get to here? And then I need to calculate what is the end location that I'm going to end up in. To do all of these things, you need to do what we have partly already done here. We calculate our normal direction vector, so this is the direction that we want to go in, and then we want to find a spot that is further in that direction. So let's say we wanted to go 1 meter past this character then, like we said in the example. What we want to do is we want to multiply this value, and we want to multiply it by a float, and then we want to multiply it by 100 because we wanted to go 100 centimeters in this case. So what we now have here is we have gone from a normalized vector to an actual real vector with length. And this is the length of the vector that is going to be from this character to wherever we're supposed to land. Now, that is not enough, because if I were to do this, if I were to disconnect this and let's do a draw debug sphere, like so. This will allow us to just draw a sphere in the world to show us where we have calculated something. This is a very useful, handy thing to do if you're trying to figure out what's going wrong with your calculations. And if I just plug this in right now here, that's going to be the center. It's going to show for, let's say, 2 seconds. Let's make it bright red. And let's have a radius of 30 or something like that. And a thickness of 5. So if we were to go in here now and press our key, you can't see what's actually going on here. You can't see the actual draw debug sphere. Now, the easiest way for me to display this is to go back to our third-person character. We can hook in our print string and our actual calculated vector, and we can also increase our radius to 100 here again, and it will be clear what is happening. So if we play again, that might not be enough. Let's do it a little bit larger. Let's try 200. Like so. Now you see that we're actually printing or drawing our debug sphere down to the right here. It's not at all where we expected it to actually be. And that is because you can see the values up in the top left there. Its values where it's showing it is 70, 70 and 002. And that is fine in the way that it is our delta, our difference that we want to charge. Because if we were to imagine that we were the target that we want to charge into and pass, then this would be the 1 meter that we said that we wanted to reach beyond him. The problem is we wanted to have it where he was, right? That's where the next part comes in. Now that we have a directionality or a vector as our delta, we need to take into account, well, where is that going to be in relation to? And we know that we're going to be charging into our target, which is our child reference over here. So if we are to add these two vectors together, let's do this a little bit cleaner, like so. This will result in the position that we're actually after. And why that is because in vector math, if you have two vectors, let's say you have one vector that goes 800 in this direction, although this character is currently now 400. So let's say it's 400 in the y direction, and you have another vector that's 400 in the x direction. If you add these two vectors together, that's like drawing the vector over here and then drawing the vector over here, which means that this is where we end up. And that's what we're doing now. We want to have the delta that we just created, that we want to run past the character, but we also want to know the location of the character. So we want to add the location of the character and the delta to find out where we end up. So let's see, did I finish this? I actually did. Let's print that over there. Let's see what we get now. So now you can see, although it's a little bit big, so let's make it a little bit smaller. Let's make it 30 again. And now you can also, you see that it's actually on the other side of the character, and you can also see that it has a better height than before, because before it was in the ground. And that's because before we said we don't want any delta in the height, in the z axis. We only want it in the x and the y. But now by adding the characters z over there of the target that we're going for, the end result of the total vector is correct in both x, y, and z as a result. So that's how we get that. And we also notice that it doesn't really matter where I run. Regardless of where I am, each time I'm clicking, I'm getting a new location for me, but we're still getting the same location over there for the other character, except for when I run something like this. You can see that it's moving around, because we said we always want to be 1 meter behind where the character is, and that depends on where we are in relation to that character. So now we have created something that has a delta beyond the character and a vector math relationship between two positions. It doesn't really matter where we are, it's always going to be correctly calculating where the end result is. I hope that made sense. Anyway, to reflect on this a little bit then, what we do is we take our two different positions. We subtract the target from our source, or the other way around, from our target from our source. And then we normalize it to get a direction. Then we multiply the direction with a float just to get a distance in that direction. Then we have a delta vector. Then we add the delta vector with where we wanted to end up to begin with, so the target character. So we have the target character and how much we wanted to rush through him. And then that result gives us our position where we want to end up in the end. I hope that makes sense. Anyway, so let's move this away and we can do something like this and say that this is direction and delta addition. Now you might end up in situations where you feel like, why is it going in the completely different direction than I expected and stuff like that. Then it's just because you're subtracting the wrong order of things. You always need to have the target minus the source to get the direction you want to go in. And if you do it the other way around, you're gonna get a vector in the opposite direction. Another good thing to keep in mind is if you at some point just wanted an inverted vector of something that you have calculated or something that you have, all you need to do is multiply it by -1 and you're going to get a vector in the complete opposite direction. Or if you have a normalized vector, that works for that as well, of course. Yeah, so next let's talk a little bit about dot products. A dot product is an ability to determine a direction towards something. Imagine if you had, for example, a game where you wanted the character to look at a specific place and to be able to detect if it was looking at that place. You might not want to be like pixel perfect and make sure that it's like looking at the exact same pixel. You might want to have some kind of leeway of like he's fairly closely looking in the direction that I want, or something like that. Something that's useful then is the dot product. The dot product allows you to determine how close you are looking towards something based on a direction. Now, to make use of this, let's use our character again. We can use our get rotation should work, I think. That's not what I'm expecting. Get, is it actor rotation maybe? Get actor rotation. There we go. Like so. Actually, we don't even need that. We can make this easier for ourselves. We can just do this. And then we get our self and we say forward vector. Let's get the forward vector of the mesh, because that's the one that's going to be most clear to us, I think. So this is a handy little thing that you can do. You can get forward vector, you can get right vector, you can also get up vector. And what this does is, like it sounds, you get the actual directionality of a certain direction in relation to something else. So if we were to print this, you can get a better understanding of what the value we get is. Like so. That's the wrong key, but it works out fine, I guess. We press E, you see it's 0, -1, and 0. So if we move around, you can see it's gonna give us different values when it comes to Y, primarily. So, how is this useful to us, you might think? Well, the forward vector is one of the components that we can use for our dot product, the actual part that is looking in a certain direction. And actually thinking about this, it doesn't look right. I think I know what it is. Viewport mesh. Yeah, you see our character mesh is actually having a rotation to begin with, so that's not ideal for us, I think. Let's do it like this instead. Let's not take our mesh, let's instead take our get our camera. Let's see if this makes more sense. x is 1, y is 0, z is minus 0. This sounds more like what I'm expecting. Minus y there, x, yeah, this looks right. So now every time I'm pressing E, I'm getting the forward vector of the camera, so where I'm actually looking. Although I have the character slightly in the way, but that's basically the point here. So we don't want to use our mesh since it's rotated a little bit. That will make our math a little bit more difficult. So let's go with the camera for now. So we have a forward vector. Now we want to know what we're trying to look at. So again, we have our child reference. And then we go actor location. Like so. And then we can do the dot product here. That's not what I wanted to type at all. Dot product. And now you could do this. And you might think that this works. But let's just start off with this and I'll show you step by step the problems. So if I'm to press now, I get a value that says 300, 300, 400, 400, 500, 500, and it then goes down. It doesn't mean a whole lot to us right now. So going back. And the reason for that is you want to have a dot product normally between like a range of 0 to 1. Or actually -1 to 1. The same as a normalized vector. And that is actually where the issue comes in here. The first part is that we have a forward vector here, and this one was actually normalized, if we remember. If we click it in like so again here, and then run, you see that all the values here are always within 1 or -1. There's nothing exceeding it. So that's a normalized vector. But we want to compare it to looking in this direction of this character, because this character now represents where we want to look. And we actually went through this before here. How do you figure out the direction? Well, you take and subtract it from the target from the source. So let's do the exact same thing over here. We don't need multiples of these, we can remove this one. So this is again our target, this is again us. So by subtracting it like this, we get our direction. But we want to normalize this as well. So we get our direction normalized. Now if you plug it in like this, and like so, you can see I get a value that is actually below 1 and not above it. So now you can see that every time I'm looking at the character, I get a value that is sort of around 1. Not exactly 1 because I need to look exactly at him for this to work. But it's fairly close to 1. If I look 90 degrees away from him, you can see that the value is getting pretty close to 0. If I look in that direction, it would also, if my mouse will let me, it won't let me. It would be 0, you can just trust me. And then in the direction backwards, the more backwards we go, the more towards -1 it will go. So a dot product will allow us to determine if we are looking directly at something by having the dot product close to 1, directly away from something being -1, like a horror game. Maybe you wanted to figure out if he's looking totally away from where I want to spawn the scary monster right now, I can spawn it safely without him actually seeing it come into the world, so when he turns around later on, he'll be surprised, right? So that's the type of thing that you could use it for also. So now that we have a dot product, we can compare it and say, well, is this equals to, and since it is a float, actually not what I want to do. I want to have nearly equal float. And then you can say I want it to be near 1, meaning I'm one is the value that I want to be near, and then the tolerance is how much you will allow it. So for example, if I were to put in 0.2, 0.2, there we go. That means that if I get anything above 0.8, so fairly looking in the right direction, then this would return true. So if we are to make a branch demonstrate this, and make sure that we only print as long as we are above 0.8, like so. Then we play. And I click and I click, nothing happens until I get over 0.8, and you can see now that it registers that. Now it stops registering because I'm not looking closely enough, and now you can see that it does it again. And then you can make sure that if you wanted it to be like, you want the character to look almost exactly at it, but not like have at least some leverage of minimum tolerance, then maybe like 0.05 or something like that. Let's try this again. You can hear that I'm clicking, and now is the only point when it actually allows it to type it out. So that is how you calculate a dot product. You have two vectors, and you can see that if you actually hover over it, it returns the dot product of two 3D vectors. So if we reflect upon this again, we got the forward vector, the way that we're looking with our camera, which is a normalized vector. We got our destination we want to compare to if we're looking at, and we're subtracting our own location. We're normalizing it so that we get two normalized vectors to compare to. We run it into the dot product, and we type out the message if it's close enough according to an error tolerance in this example. I hope that made sense. Dot product, like so. I believe these three situations, or these three approaches, will be able to handle most of the math that you want to be able to do when it comes to dealing with math in a game engine. If you feel that I'm missing something, feel free to let me know, and I'll try and make a little bit more advanced version covering more vector math. But I hope that this was both understandable and educational and useful to you in your own projects. Hopefully you found this video helpful. If you liked the video, leave a like. If you did not like it, leave a dislike. Leave any suggestions or comments you might have down below. Subscribe and share this video if you want to see more like it in the future. That is all for now. Keep on learning. Take care.